This is a tutorial for problem 9.P.38 from Matter and Interactions, Volume 1. So in this problem we have a hoop of mass capital M and radius capital R rolling down a hill without slipping. It has some initial speed, Vi, or its center of mass has that initial speed. It's at the top of a hill of height h. We want to know how fast it's translating, or what's the final center of mass velocity at the bottom of the hill. So here's our picture. It's pretty simple. Got the hoop rolling down a hill. If this were simply just an object sliding down a hill, it would be a lot easier because then we wouldn't have to take rolling into consideration. But since it does roll, we need to have a kinetic energy term for rolling. Okay, so let's see how we can set this up. Well, energy is definitely conserved. There's no frictional loss here. So we will set up basic energy equation. Alright, and those are our energy terms. In the final state, it's translating and rolling, but has no potential energy. So we have these two terms. In the initial state, it's translating, rolling, and has gravitational potential energy. So now let's try to fill in each of those terms. Alright, those are all the terms we have. There's regular kinetic energy, which is 1/2 mv squared in the final state and in the initial state. Then rolling energy is 1/2 I omega squared. I is the moment of inertia. Omega is the angular speed. So we have that in the initial and final states. And we also have gravitational potential energy in the initial state. So that's this term. What we can do now is use the fact that we have a hoop, and that means moment of inertia is mr squared. And also it's not slipping, as it tells us in the problem, so the angular speed is just the center of mass velocity divided by the radius. And for an explanation of why that's true, you can consult the text. Okay, so you can see I substituted mr squared for the moment of inertia and VCM over r for omega final, using the final center of mass velocity or the initial center of mass velocity, depending on whether we're talking about the final or initial state. Now what we want to do is solve for VCM final. That's what we're looking for. And notice a few things happen. Well, we could multiply everything by 2 to make things a little bit easier. And notice also that r squared cancels with the r squared here, and likewise over here. So the next step looks like that. And also all the capital M's cancel. So then we arrive at the answer. Now let's move on to part B. Now things get a little bit complicated. So instead of a hoop, we have a bicycle wheel, as shown in the bottom figure here. And now it has a hub in the middle of mass little m. The spokes have negligible mass. Now what's the final speed of the bicycle wheel? This would be our diagram now. The reason this gets more complicated is because we won't get as much cancellation in the equations, as you'll see in just a sec. So we'll start again the same way we started before, with energy conservation. And now let's fill out those terms and see what's different. And notice now the moment of inertia is actually the same as before, because the hub doesn't add anything to the moment of inertia. The hub is at a distance 0 away from the center of mass, so there's no moment of inertia associated with that hub. Consequently, those two kinetic rolling terms are actually the same as before. Alright, now let's factor out VCM final. and I also factored out VCM initial, and I multiplied the previous equation by 2. Okay, so we can get some cancellation here if we divide by this term, the 2m plus m, although not all the masses will cancel as they did in part A. And there we have our final result. One thing we should make sure to check is that if the mass of the hub, little m, is small, we should recover our answer for part A, because then we just get a hoop again. So let's see if that happens. Well, if little m is 0 here, so little m would drop out here and here, so then we'd have 2m gh over 2m, which would just be gh. So this whole term becomes gh, and lo and behold, it's the same as before. Another interesting question we might want to answer now is, which one's going faster at the bottom? Is it the hoop or the bicycle wheel? Well, first let's just see that from the math. Notice the numerator here is bigger than the denominator because we have an extra factor of small m up here. So actually this term is larger than gh if little m is not 0. So that means that the bicycle wheel is actually rolling faster at the bottom. Well, how can we understand that? We can understand that by looking just at the energy equation. Maybe I'll put that again down here. If you have a mass in the middle, little m, then that's going to carry some translational kinetic energy. So relatively speaking, the bigger that mass in the middle is, the more translational kinetic energy we'll have relative to rotational. In fact, let's just look at the simplifying case where little m is really big, much bigger than big M. In that case, the rolling component of kinetic energy is negligible because almost all the energy is going to be in the hub. And then the problem drastically simplifies. Actually, now it's the same as a block sliding down a hill with no friction. So we can solve this really easily. And I trust that you can solve for that yourself. So that's if the hub has basically all of the mass, you get the same thing as a block sliding down the hill. And that's faster than the hoop rolling. Actually, the block sliding down the hill would give you the fastest speed because all of the energy is translational in that case, and you're not rotating at all. Notice one thing further, that this equation simplifies to this equation if we simply take small m to be very large, because then we can ignore the capital M terms here and here, so we get 2 little m over little m, which is 2gh, and that's the same as this equation. Okay, so there are a lot of interesting limits that we can consider in this problem.